Virtual prototyping is a technology for modeling the functionality of ASICs using a high-level language such as System-C, which enables architecture and performance analysis of the ASIC design. Within the virtual prototype, the various functions of the ASIC are modeled with abstracted functionality and cycle-accurate, transaction-oriented interfaces. These models are then executed in a cycle-based simulator that mimics real-world behavior of the system. This type of simulation runs much faster than an RTL simulation and allows more system aspects such as memory congestion and traffic throughput to be analyzed. Building a virtual prototype will enable architecture and performance analysis, power analysis, and even software development earlier in the ASIC design process than was previously possible. This allows refinement of the architecture prior to RTL coding, thus reducing effort due to redesign. Early software development can begin well before hardware prototypes or silicon are ready, further reducing overall schedule. We'll look at each of these capabilities in more detail. The goal for architecture and performance analysis is to refine the architectural aspects of CPU, interconnect, and memory subsystems with respect to clock speed, bit width, cache, and memory capacity prior to RTL implementation. Architectural refinements during this stage help avoid over-design or under-design of the RTL, which in turn helps to avoid costly redesign. This type of analysis is most useful for systems that have multiple high-speed interfaces and/or coprocessors accessing shared resources such as the interconnect and main memory system. The fact that this is a dynamic simulation of actual behavior, we can see the real-time effects of contention for the shared resources, which help identify the system bottlenecks. By varying parameters such as clock speed, bit width, and cache capacity, the architect can explore variations on the original design and see how the performance changes, where the architecture breaks, or how much margin is available. For power analysis, the virtual prototype can be simulated with a real-world application, and utilization information can be extracted from each of the active models. In many cases, CPU models come with thread profiling and power state profiling to assist with analysis of real-time power behavior, as shown in this screenshot. Additionally, transaction monitors may be placed on the interfaces of each functional block and can be used to accurately measure utilization of both the logic and the interconnect. This information can be applied to library information for the target silicon process to determine the actual power consumption. Early software development can be done on a virtual prototype once the RTL design is complete and converted into a fully functional System-C model. Software engineers can develop, run, and debug boot code, bare metal test code, hardware drivers, and even boot a minimal OS. Since the virtual prototype has identical functionality as the ASIC, this early code will port directly to silicon. As shown in this diagram, the software development environment is the same as what is typically used for an embedded system, and in this case, an embedded ARM CPU. With the virtual prototype, much of the software needed for silicon bring-up and validation may be developed ahead of time with high confidence that it will work. Open Silicon utilizes a number of tools to create models and simulation systems that comprise virtual prototypes. From Carbon Design Systems, we use Carbon SoC Designer and Carbon Model Studio. SoC Designer is a tool for capturing the system design and also for executing the cycle-based simulation. Model Studio is a tool for converting RTL designs into System-C models, which can then be imported into SoC Designer. Carbon also provides an extensive library of pre-compiled and configurable models of IP from numerous providers, including ARM, Cadence, and CEVA. Open Silicon also makes use of ARM CPU fast models to accelerate simulation speed for virtual prototypes that are designated for software development. These models trade off cycle accuracy for simulation speed, which is beneficial to the software development environment. Open Silicon develops custom external memory models and uses third-party peripheral models, Cadence and Synopsys, to implement the external functions needed for a full system virtual prototype. With virtual prototyping, we can make architectural refinements very early in the design stage in order to meet performance and power consumption goals and avoid costly redesign. We can also enable early software development in parallel with the ASIC layout and fabrication process, and further accelerate the ASIC bring-up process with debugged code ready to execute when the silicon arrives back from fab. Overall, the use of virtual prototyping will reduce the design schedule and increase the quality of the design throughout the development process. If you are interested in more details, please see the related videos in which I present live demonstrations of example virtual prototypes and how they are used for architectural analysis and early software development. Thank you for watching.